Hello all, welcome to the seventh lecture. The last time we met, we spoke about an electron in the Dirac comb. Uh, I think we first saw about electron in an delta potential, and we started to deal with periodic structures. But before we dive deep into the physics of nanostructures and physics of crystals and lattices, let us take a small detour and talk about what are crystals, how they are grown, what are the typical methods in which they are grown. And when we talk about 3D bulk materials, 2D layers, thin films, nano wires, and nano dots, then there will be something for you to think about. Okay, so we will spend some time to talk about materials and processing. That will be the topic of this video. The most common crystal or single crystals, as we call about, is silicon. Right, semiconducting materials have been made to this great levels of purity and such reduced levels of defects that they are special in all kinds. For instance, silicon has a purity of 9 nines, in the sense that it is 99.9999, something like 9 nines pure. There is only one part in a billion that the silicon atom will be replaced by some other impurity. Okay, a silicon, even which is that pure, costs only about $29. Gallium arsenide, another single crystal, costs about $58, while a gallium nitride single crystal, so this is a gallium nitride single crystal wafer, costs about $2,500. Now, why does it cost so much? Gallium nitride is another important semiconductor which is used in power electronics and such. Okay, while gallium nitride as a single crystal wafer costs so much, there is something called as an epitaxial stack, where gallium nitride is grown on top of another material. It costs about $535. You can see the stark difference in the prices. That's because of the difficulty in which they can be grown. Other common material like graphene costs about $300 for a 2-inch wafer and such. But this is not of a particular concern for this lecture. Okay, so it's only about these materials, these semiconducting materials, the difference between silicon, gallium nitride single crystals, gallium arsenide single crystals, and gallium nitride epitaxial stacks grown on materials like silicon or sapphire. Okay, this will be what the topic of today's discussion will be. Why are they so expensive? Why are some metals expensive, some semiconductors expensive, some cheaper? It's because there are two different kinds of growth. One is growth from melt, another one is epitaxial growth. Growth from melt, there are only some materials which are grown: silicon, germanium, indium phosphide, and gallium arsenide. That's because of their melting temperatures. If you see here, silicon melts at about 1685, gallium arsenide at 1510, and germanium somewhere around 1231. Okay, these temperatures are easily accessible, and you can also grow them or get them in relative purity. We will see how to get silicon in relative purity. Other materials can also be obtained in relative purity, so that you can get a melt of very good quality, and then you can grow something from the melt. Other materials like gallium nitride, silicon carbide are mostly grown by epitaxial means, and you also have gallium arsenide and algas grown by epitaxially, because you typically need very thin layers. We will see different techniques in which you can grow epitaxial layers. One method is called liquid phase epitaxy. You have vapor phase epitaxy, you have molecular beam epitaxy, and you have some metal organic MBE. MBE is molecular beam epitaxy. Metal organic is the source metal metal organic means, let's say for gallium, in gallium nitride, it is trimethyl gallium is the source. So methyl being the carbon, organic material, right? You have a metal and an organic, so it's called metal organic chemicals. Okay, but before we jump into the actual growth and such, one has to understand what are phases and what is equilibrium. This is something which is very important in crystals. So phase is something, a region which has uniform material properties. For instance, here we have a phase diagram of water. Water exists in three stable phases. One is ice, solid, water that we call the liquid, and then the vapor. right? And at each temperature, there is a particular, so at each pressure, there is a temperature at which the ice or the two phases stay at equilibrium. What it means is that if I take, let's say, a volume of water and have an ice bar here, right, at some particular temperature T, at any pressure P, let's say we call it at 1 atmospheric pressure so that we know the temperatures, right? Let's say we are at 1 atmospheric pressure, normal atmospheric pressure, okay? And we have an ice cube here. At T greater than 0, obviously the water molecules in the ice cube wants to leave the solid phase and go down to the liquid phase, right? Water starts to melt. So at this temperatures, anything, if you are here, water wants to be in the liquid phase, so there is a spontaneous movement of molecules from the solid phase to the liquid phase. If T is lesser than 0, you are somewhere here, right? And the water molecules now move from the liquid phase to the solid phase, and you will see the solid block growing in size. The same thing will happen if you do if you change the temperature at constant pressure in silicon. Let's say I draw a line here. Let's say you are again at 1 atmosphere. If I take silicon and then melt it at about 1600 degrees, it melts and forms a liquid. And if I can cool it down below this temperature, then it forms a solid silicon bar. About how it forms the solid silicon bar and how you cool down determines the quality of the solid. You can have a highly ordered crystal if you can cool it down in a well controlled manner. And this is what is the basics of the Swarovski's process. So first thing, the first example that we will see will be 3D crystal growth from seed, which is the most common process that you would have seen. We always start with sand. They say you can start with sand, but that is not true, because to begin with this Swarovski's process, you need 9 pure silicon. How do you get it? You take sand, you treat it with coke, and then you treat it with HCl, and then you treat it with, and then you break down the salt to give you silicon. This will be done several times to get what is called as polysilicon. It is called poly because it is polycrystalline right now. There are a lot of defects, there are a lot of boundaries, so there is no lot of order. I take this polysilicon, I melt it down. How do I melt it? I heat to temperatures greater than the melting temperature at atmospheric pressure, right? And then I get this molten silicon. Now if I introduce a silicon crystal into it and then slowly pull up, so what happens is, let's say I again draw this here. Let's say I get molten silicon here and I bring in a bar of pure single crystal silicon, right? And there is surface tension and capillary forces which will make the silicon to bend up, right? Silicon will like itself more than air, so silicon will try to rise above the surface along the lines of the silicon bar. This is because of surface tension. It's also called as capillary forces. So the silicon, instead of being a flat surface, will now form this. And as you see, the temperature here will be much smaller than the temperature here, and the silicon at these regions will start to melt, and then it will start to crystallize. If you are able to do it very slowly and if the temperature is well controlled, you will get a solid silicon ingot, right? The temperature here I have written as 1500. It is typically 1650 C or such. It of course depends upon the pressure in which you are operating, right? So this is the basic of growth using the Swarovski's process. However, it is not this simple, right? To get a very good quality silicon, you need to rotate both the seed crystal as well as the crucible. And the relative, and people typically establish a relative speed between the seed pull out as well as the crucible to have a uniform temperature distribution in the crucible. This is the molten region. One has to maintain a uniform temperature and the velocity of these molecules, right? So this is the temperature, and this is the velocity profile. You want the entire crucible to have a uniform velocity so that it is uniformly distributed, and temperature to have a uniform value. You can see that if you can maintain one particular relative rotation speed between the crucible and the seed, then you can have well-defined growth. And this is what typically is done in Swarovski's process, right? Well, you can actually go into details about how the crystal growth actually happens and how it nucleates. But for the purpose of this lecture, I'll probably skip this. What I just wanted to enforce or drive home here is that there are two ways a crystal growth can happen. It can happen homogeneously, which is called as a homogeneous nucleation, right? The second thing is heterogeneous. It can be known, I just want to drive this particular point, that if you have a growth of a new phase or solidification from a melt happening on a pre-existing substrate, then the del G is a Gibbs free energy. The energy to nucleate is much smaller than the energy that you require to grow in a homogeneous fashion. If I repeat, the energy to nucleate a new phase on top of a pre-existing phase is lower than the energy to nucleate a new phase homogeneously without an assist of a substrate. Of course, it depends upon whether the new phase likes the substrate or not. So that's where the choice of the substrate comes, right? So this is what we call as a parent phase, and then you nucleate a new phase. If it grows without the aid of a substrate, you call it as a homogeneous nucleation. If it grows with the aid of the substrate, it is called as heterogeneous nucleation, which grows like this. If you can choose the substrate well, then you will have a better growth. The example of a heterogeneous nucleation is epitaxy. Epitaxy means growing one layer on top of the other. Now you can do it in two ways. If the layer that you grow on top of the substrate, so we call this the layer which you grow as a film, and the layer on which you grow, it is called as a substrate. Okay, yes. If the layer that you grow and the substrate belong to the same material family, it has the same lattice constants. Each of these square is a unit cell. I suppose you must have heard about unit cells probably in your first semester, right? If the unit cell between the film and the substrate does not differ a lot, the unit cells are well matched, you have what is called a homoepitaxy. You get a heteroepitaxy when they are not matched, when typically happens when you have dissimilar materials, right? And initially, as the material grows, you get what is called as a strained heteroepitaxy. You get a strained film, or if the strain is too much, you nucleate a defect at the surface. It is called as a relaxed film. A typical relaxed film almost always have defects at the surface, which has several impacts. It can affect the electron transport, so on and so forth. You will always have defects at the interface. While the strained film does not have any defects, it grows almost pristinely, but then the material has a compressive or a tensile strain. The origin of the compressive or tensile strain can be understood by understanding the lattice misfit, which is defined here. So lattice misfit is defined as a ratio of the difference in the lattice constant A0S minus A0F by the A0F, F being the film, S being the substrate. So it is measured, so it is typically expressed as a ratio or a percentage of the material which wants to be grown, or the percentage of the misfit with respect to the film, right? So take this example. Here I grow, let's say, silicon on top of silicon germanium. Silicon germanium lattice constants is bigger than the silicon, right? So now if you grow on top of the other, you can clearly see the silicon lattice will have a tensile strain, right? The silicon film will be pulled apart. Whereas if you grow other way around, if you grow silicon germanium on silicon, the silicon germanium will have a compressive strain. Whenever there is strain, there is a total built up strain energy. The thicker the film you grow, larger will be the built up strain energy. And if the built up strain energy is larger than the dislocation creation energy, you start to create dislocations as shown here, and the film will start to relax. You will start losing this strain because now you are creating defects. As you create the defects, then the lattice will relax now, going back to its equilibrium distances, right? So here I have plotted, or people have plotted, the maximum thickness that you can grow without nucleating defects for various germanium fraction in silicon. So this is the fraction of germanium in silicon, which is Si1 minus x GeX. As I increase germanium fraction, you can clearly see the maximum thickness that I can grow drops down significantly. And if it is 0, you can grow theoretically infinite thickness of silicon on top of silicon germanium. Right? Now, these epitaxial films are being conventionally used in many places. This is one particular example where people have grown N gas. They have taken the N gas substrate. They have deposited another heavily doped gas layer. They have deposited an all gas layer. They have deposited again an undoped or intrinsic gas layer. Then the p-type gas, all gas, and the p-type gas and the chrome contact. You can see the number of materials that have been used and its thicknesses range from about 500 nanometers to 2 microns and such. This is used for light emission. Can you guess where the emission would happen? It would obviously happen in the undoped region, right? So this is the region in which it will typically happen. So the probable place the light will be emitted maximum is in this region, in the intrinsic layer, right? Now let's look at some ways in which you can grow these epitaxial stacks. As we said before, there are several ways. One most easiest way is liquid phase epitaxy. Epitaxial layers typically depends upon the lattice constants. So here we plot the lattice constants versus band gap for several important materials. One material to be noted is the gauze and the aluminum arsenide layer, and anything in between is obtained by replacing gallium atom in gauze by an aluminum. So in these layers you get what is called as all gas layers. If you replace a gallium atom by an aluminum atom, you'll get an all gas layer, right? The interesting aspect of this is as you go from gallium arsenide to aluminum arsenide, as you change the gallium percentage from 0 to or 1 to 0, you see that the lattice constant barely changes. So this set of materials, gauze, all gas and aluminum arsenide, is great for epitaxial growth purposes, and that is why it is being used in many light detection and light emission applications. And another important material system is indium gallium arsenide, which exists in this layer. As you can see, there is a huge variance in the lattice constant, so it is typically not used with varying concentrations of this. The most common concentration exists here, which is about gallium about 0.47 and indium 0.53. Under these concentrations, you can see that it can be grown epitaxially on indium phosphide. So indium phosphide is important because it is a semiconductor whose melting point is low. So you can actually grow indium phosphide using a bulk crystal from melt method, as we saw previously. And on top of an indium phosphide substrate, you can grow an InGaAs layer. Okay. So with these things, let's see how you can grow an epitaxial layer using liquid phase epitaxy. What people do is they take a melt, and let's say if you want to deposit an gas layer, they take a molten gas or molten gas, anything with the known concentration in any of these places, and then you introduce the substrate right below this. So what happens, let's say you are at this point. So this is a liquid phase. Here you have a liquid phase, and below this line you have a solid phase, right? So you take this this region, melt it above the liquidous line, and if you introduce a substrate very close to the substrate, of course the temperature will drop, and then you will deposit a solid material there. Of course it's much more complicated than how I explained, because even at this temperature you can see that there is some equilibrium concentration of liquid and some equilibrium concentration of the gas layer. So the amount of gas being ejected out of this liquid system depends upon what is the composition of the arsenic, what is the composition of any other dopants that you have added. Right? Let's not go into this, but this is just one way to deposit by a cheap way thin films of semiconductors epitaxially on top of another substrate. It has poor uniformity and it has rough surfaces, but it's among the cheapest method to deposit an epitaxial layer. The next way to deposit very thin layers in a controllable fashion is vapor phase epitaxy. What they do is they take a substrate like silicon wafer here, keep it in very high, very low vacuum levels or very high vacuum levels, and bring it to a particular temperature. If you send in suitable gases, these gases will react and then deposit the material. One way to deposit gas again is to use trimethyl gallium with arsine. So I take arsine, react with trimethyl gallium at some controllable temperature like 650 to 700. You will deposit a gallium arsenide film. Because this uses a metal organic source, it is also called as MOCVD, metal organic chemical vapor deposition system. There is no contact between the substrate and the reactor. Very thin layers are possible. You can also obtain sharp transitions. It is not a very expensive process and it can be easily scaled. This is why CVD and VPE are one of the most commonly used equipments in commercial fabrication places. 2D nanostructures like super lattices and quantum wells are most often grown by this MOCVD process. This is one stack which is used as a VCSEL or I'm not sure, it's called vertical cavity lasers. All the solid state lasers, light emitters, light emitting devices, photodiodes are all grown by MOCVD methods. Right? So these are examples of ultra thin layers or 2D nanostructures. Here only the thickness is confined. You can have really large lateral dimensions but very thin or nanoscale thickness dimension, right? That makes it a true 2D structure. Molecular beam epitaxy is another way in which you can grow really thin layers, something whose thickness is lesser than probably few nanometers, right? Like 10 nanometers, something lesser than 10 nanometers. The idea is they will grow monolayer by monolayer. You have several sources which can be independently controlled. So what they do is they start passing the independent metal sources and then the gas source in very small fractions, and they will let it grow by a layer by layer method. The schematics is shown here. Let's say you take a plain substrate, you will nucleate first one material and then the second material and then the third material, and then you will form one complete monolayer by these steps, and then you go back here and then do the second monolayer. In this fashion you can have very controlled number of layers, very high material purity, as well as control on what is doping density and uniformity and so on and so forth. Right? It's obviously the most expensive method and hence is mostly used in research environments, rarely in commercial places. Now that we have seen how 2D structures are made, here is an example of how you can make 1D structures. Carbon nanotube is one of the most famous 1D structure. The most common way to grow it is to have catalyst lines, right? So you have metal catalyst and then you pass methane. You can see very well aligned vertical nanotubes. Nanotubes are typically used in transport applications like this. So here you have two metal lines, you have nanotubes in between, you have gate on top. You apply, this is a standard MOS structure. You apply potential and change the transport characteristics of the tube, and then you can use it for logic applications. But these things are still in research phase. The most common use of these 1D structures is in silicon nanowires. These have applications in artificial sensors, artificial let's say noses and such. The most common way to grow this is called a VLS or vapor liquid solid method. You take a metal droplet and then you have a very high partial pressure of the source gas. In case of silicon, you use silane. In case of carbon nanotubes, you just use methane. any of these sources will break on top of the metal nanoparticle. It will leave behind silicon or carbon appropriately, and they will nucleate below, and the wire will grow from the bottom. Like as you can see here, these round things on top are the metal particles, and as time progresses they will just grow vertically from the bottom, right? So this is one way to grow nanowires. The last nanostructure that we will see is the 0D nanostructures, which is also called as quantum dots. They have applications in optoelectronics, the most famous one being cadmium selenide, cadmium sulfide, indium arsenide, cadmium telluride, and such. They are much easier to grow than the 2D structures and 1D structures that we saw previously. All you need is to pass the metal precursors into a solution of probably in a solution containing chalcogen, or probably you will send the chalcogen independently. You will nucleate nanoparticles and then cap it with a suitable cappant so that it will not grow any further. You can control the dimensions. The typical dimensions range from 10 to 100 nanometers, and it has real good applications in optoelectronics, right? So now that we have seen practically the nanostructures which can be formed or which can be practically realized, let's go back and study some physics about these nanostructures. What can we expect from the, let's say, for example, take indium arsenide. Indium arsenide exhibits or exists in various structures, right? It can have it can be it can exist in bulk wafers. It can come in 2D layers. It can also form 1D nanowires as well as 0D dots. So what can you expect as you go from 3D to 2D to 1D to 0D? So these are the aspects that we will try to bring out during the course, and I hope this introduction to the material system helps. With this, I thank you for the attention. Let's meet next time. Bye bye.